Have you ever wondered about the reddish-brown metal that's literally everywhere? From the pipes bringing water to your home, the wires powering your devices, to the very coins in your pocket, copper is an unsung hero of our modern world. But where does it all come from? How do we get from a rock in the ground to a shiny, pure copper wire? Today, we're going on an incredible journey to uncover the secrets of how copper is made. It's a story of fire, chemistry, and incredible engineering. Let's dig in. First things first, you can't just find pure copper lying around most of the time. It's usually locked away inside rocks called ores. The most common copper ore is called chalcopyrite. It's a mix of copper, iron, and sulfur. To get the copper out, we have to mine these ores. This is a massive operation. Miners use huge machinery to dig deep into the earth in open-pit mines, which look like giant, terraced craters where they venture into underground tunnels. The goal is to get truckloads of this copper-rich rock to the surface. But here's the thing. The amount of actual copper in these rocks is tiny, often less than 1%. Imagine having a 100-pound rock, and only 1 pound of it is copper. The rest is just waste rock. So the first major step is to concentrate the ore. This process is called froth flotation. The mined ore is crushed into a very fine powder, almost like sand, and then mixed with water and special chemicals. When air is bubbled through this mixture, the tiny copper-containing particles stick to the bubbles and float to the top, forming a froth. It's like a metallic bubble bath. This froth is skimmed off, and just like that, we've gone from less than 1% copper to a concentrate that is about 25 to 30% copper. We've successfully separated the good stuff from most of the waste. Now we have a much richer concentrate, but it's still not pure copper. It's mixed with iron and sulfur. The next step is to get rid of that sulfur. This is done through a process called smelting. The concentrate is heated to extremely high temperatures, over 2,000 degrees Fahrenheit, in a massive furnace. This intense heat causes a series of chemical reactions. The iron and sulfur in the concentrate combine with oxygen from the air and with other materials added to the furnace, called flux, which is usually silica. They form two main products. One is sulfur dioxide gas, which is captured to prevent pollution. The other is a molten liquid waste called slag, which is mostly iron silicate. What's left is a molten pool of something called copper matte. This matte is much richer in copper, now around 60%, but it's still a mixture of copper and sulfur. We're getting closer. The molten copper matte is then transferred to another furnace called a converter. Here, more air is blown through the molten liquid. This is where the magic really happens. The oxygen in the air reacts with the remaining sulfur, turning it into sulfur dioxide gas, which escapes and is collected. As the sulfur leaves, what remains gets more and more pure. As this process nears its end, the escaping gas creates bubbles in the solidifying copper, making its surface look rough and blistered. Because of this appearance, the product at this stage is called blister copper. We've made a huge leap. Blister copper is about 99% pure copper. For many applications, this might be good enough, but for things like electrical wiring, we need it to be even purer. Even a tiny impurity can significantly reduce copper's ability to conduct electricity. So we need one final, crucial step to get it to that ultra-pure state. This final refining process is called electrolysis. It's a bit like running the whole process in reverse, but with electricity. The blister copper is cast into large, thick plates called anodes. These anodes are then submerged in a tank filled with a special acidic solution, an electrolyte bath made of copper sulfate and sulfuric acid. Alongside them, thin starter sheets of pure copper are also placed in the tank. These are called cathodes. Then we pass a powerful electric current through the tank. The electricity causes the copper atoms from the impure anode plate to dissolve into the electrolyte solution. These dissolved copper ions are positively charged, so they are attracted to the negatively charged cathode sheets. They travel through the solution and plate themselves onto the pure copper cathodes, one atom at a time. It's an incredibly precise process. The cathodes grow thicker and thicker, built up from layer upon layer of ultra-pure copper. But what happens to all the impurities that were in the blister copper? Things like gold, silver, platinum, nickel, and lead? Well, they don't dissolve and travel like the copper does. They simply fall off the anode and settle at the bottom of the tank as a sludgy substance called anode slime. And here's a fascinating bonus. This slime is actually valuable. It's collected and processed to recover precious metals like gold and silver. So making pure copper also produces other valuable metals as a byproduct. After several weeks in the electrolytic bath, the original impure anodes have been mostly eaten away, and the cathodes have become thick slabs of incredibly pure copper. We're talking 99.99% pure. This is the high-quality copper needed for electronics, telecommunications, and power transmission. So let's recap the amazing transformation. We started with a rock containing less than 1% copper. We crushed it and used froth flotation to create a 30% concentrate. Then, we used smelting to melt it down and remove most of the iron and sulfur, creating a 60% copper matte. After that, the converter blew out the remaining sulfur to produce 99% pure blister copper. And finally, through the elegant process of electrolysis, we used electricity to purify it atom by atom, reaching an incredible 99.99% purity. From the mine to the mill, from the furnace to the refinery, the journey of copper is a testament to human ingenuity. It's a multi-step, energy-intensive process that turns a common rock into one of the most essential materials of our civilization. The next time you flip a light switch or turn on a tap, take a moment to appreciate the incredible science and engineering that brought that silent, conductive metal into your life. Thanks so much for watching this deep dive into the world of copper. If you found this journey as fascinating as I did, be sure to hit that like button and subscribe for more explorations into how our world works. Let me know in the comments what material you'd like to see us cover next. Until then, stay curious,